Hello. Our aim in this video is to find the antiderivative of the function square root of x plus 2 times cosine of square root of x plus 2. This is a typical calculus 2 problem. We will carefully walk you through the solution. When we look at this problem, it is clear that this is a complex integration question. Whenever you are confronted with this type of problems, it is important to devise a strategy to attack them efficiently. It is always beneficial to analyze the function that we are asked to integrate. This initial analysis of the function will help us figure out the proper strategy to solve the problem. In this case, the function square root of x plus 2 times cosine of square root of x plus 2 is a product of a radical function square root of x plus 2 and a composition of two functions, the cosine function and the square root function. Because this product involves a radical function and a composition of a nonlinear function with the same radical function, it is a good idea to start with the method of substitution. We will perform a change of variable, we introduce a new variable. It is evident that the natural choice for the new variable y should be the inner function. Thus, y should be square root of x plus 2. So, we set y equal to square root of x plus 2 and dy should be equal to 1 over 2 times square root of x plus 2. The integral of square root of x plus 2 times cosine of square root of x plus 2 dx can be expressed as the integral of 2 times square root of x plus 2 times square root of x plus 2 times cosine of square root of x plus 2 times 1 over 2 times square root of x plus 2 dx. We can clearly see y and dy in the expression of the integral. So, we replace square root of x plus 2 by y, and 1 over 2 times square root of x plus 2 by dy. We then obtain the new expression of this integral as the integral of 2y square times cosine of y dy. This new expression of the function to integrate is simpler than the original one, however we still have to carefully figure out the best way to integrate this new function. This new function is the product of a polynomial function, 2 times u square, and the nonlinear function, cosine of y. Observe that, the best method for the integration of products of polynomial functions and nonlinear transcendental functions is the method of integration by parts. In this case, we have to use the integration by parts method to compute the integral of 2y square times the function cosine of y dy. Please do not forget to like the video and subscribe to our channel. Thanks to those who have already done so. Let us integrate the function 2y square times cosine of y. Notice that, at first glance, we easily see that the function we have to integrate is a product of a nonlinear function, cosine of y, with a polynomial function 2y square. Sometimes, when you are faced with this type of complex integration problem, you have to adopt the appropriate strategy that will help you simplify the problem and find the antiderivative efficiently. The two main techniques that we learn in Calculus 2, for solving integrals that involve the products or quotients of nonlinear functions are the u-substitution method and the method of integration by parts. The crucial first step of our strategy is to decide which of these two classical methods we should use. In this case, we have a product of a nonlinear function with a polynomial function, so the best method to use is the method of integration by parts. Because this method will help us reduce the complexity of the problem by reducing the degree of the polynomial. Actually, the polynomial function 2y square is of degree 2. Consequently, our first goal will be to reduce the degree of the polynomial function to 1, by using the method of integration by parts. Let us briefly review the method of integration by parts. We know that the integral of u dv is equal to u times v minus the integral of v du. Then, we set u equal to 2y square, so du equals 4y dy. And, dv equals to cosine of y dy, and v equals to sine of y. In sum, the integral of 2y squared times cosine of y dy is equal to 2y squared times sine of y, plus the integral of minus 4y times sine of y dy. Consequently, we still have to integrate minus 4y times sine of y, using integration by parts. Let us integrate the function minus 4y times sine of y. Given that the function to integrate, minus 4y times sine of y is still the product of a nonlinear function with a polynomial function, we still have to use the method of integration by parts. The main aim of these repeated utilization of the method of integration by parts is to reduce the degree of the polynomial function, minus 4y. Therefore, we set u equal to minus 4y, so du equals minus 4 dy. And dv equals to sine of y dy, and v equals to minus 1 times cosine of y. Finally, the integral of minus 4y times sine of y dy is equal to, for y times cosine of y, plus minus 4 times sine of y, plus a constant c. Now we have to aggregate the results of these repeated applications of the integration by parts to get the final value of the antiderivative of 2y squared times cosine of y. The first integration by parts gave the following result. So, the integral of 2y squared times cosine of y dy is equal to 2y squared times sine of y, plus the integral of minus 4 times cosine of y dy. From the second integration by parts, we obtained the following result. So, the integral of minus 4 times cosine of y dy is equal to, for y times cosine of y, plus minus 4 times sine of y plus a constant of integration c. As a result, combining the last two results, we see that the integral of 2y squared times cosine of y dy is equal to 2y squared times sine of y, plus 4y times cosine of y, plus minus 4 times sine of y plus a constant of integration c. In sum, when we replace y by square root of x plus 2, we see that the original integral of square root of x plus 2 times cosine of square root of x plus 2 dx is equal to 2x plus 4 times sine of square root of x plus 2, plus 4 times cosine of square root of x plus 2 times square root of x plus 2, plus minus 4 times sine of square root of x plus 2 plus a constant of integration c.